Okay, now that we've learned all about what a polynomial is and what we might call its anatomy, right? Anatomy kind of means what makes something up. And we've also even learned some interesting applications. Now, we didn't talk about the word polynomial, but we've looked at how we can use a polynomial and the coefficients and the pieces of it to help predict or figure out certain situations, like when we did the rolling dice. And that can also help us figure out some probabilities of what will likely happen. So they're actually very useful, but they are very heavy in vocabulary. So that's why it's important we're spending so much time on that. So our prior knowledge will be all the polynomial vocabulary from our last video. So degree, term, like terms, coefficient, and constant term. And it will be helpful for you to remember like some rules about exponents and how they work or how they don't work, especially. And we're going to revisit multiplying expressions because our actual lesson today is on operations on polynomials. And if you remember, the four basic operations are adding, subtracting, multiplying, and dividing. We're going to kind of focus on adding and subtracting today. We've already done a lot of work actually on multiplying expressions. We didn't call them polynomials before, but if you think about it, all of the expressions we've been working with lately are actually polynomials. So we've got quite a bit of practice on multiplying. We'll do a little more still today. And before we actually get into our main, I guess, new examples, I think it's important that we do some warm-up here. And there's, you know, a little bit longer or more maybe than our normal warm-ups are, but I think it's going to be very helpful. So again, because this is a warm-up, it means it involves something we've learned before. And what I want you to do right now, please, is pause the video and do the work on your own, and then you can compare your work to mine. So please pause now. Okay, let's go ahead and take a look at what you came up with for these problems. Now, one says, show or explain why 3x squared plus 4x is not equal to 7x cubed. Well, let's think about a few things. If we're trying to show something works or doesn't work, something that's often really helpful is using a specific example. So what I mean here is, did you try to just plug a number in for x and see that it does or doesn't work? In this case, we're trying to show something doesn't work. And showing something doesn't work is actually a lot easier than showing it does work, right? And I've probably said this before, but if I asked you if I made this statement, oh, all apples are green, you'd probably be like, wait a minute, here's a red apple, right? And you can use one example to disprove something. That will always disprove. If I wanted to prove all apples were red or whatever, which they're not, but you'd have to physically figure out a way to convince me or show me that every single apple was that. And that's way more difficult, right? So in this case, if we just come up with one example, that's going to be enough to reason through why this doesn't work. So anyway, I don't know, what should we choose? Maybe 2? Let's see what happens when x is 2, okay? So when x equals 2, then we get 3 times 2 squared plus 4 times 2, right? And that is equal to, remember our order of operations, exponents first. So 2 squared is 4, times 3 is 12, plus 8, which is 20. And this guy right here, if x is 2, becomes, 7 times 2 cubed. And again, don't forget our order of operations. 2 cubed is 8, and 7 times 8 is 56. And clearly, 20 does not equal 56. So I'll write it over here, that 20 does not equal 56. And actually, you'd find that lots of numbers you tried to plug in there would never equal that. And if I'm not mistaken, there is not going to be a nice whole number that will ever make this particular one that I chose be true. Okay, so testing numbers is really helpful to disprove something. Now, in the bigger picture here, why did I even ask this in the first place? Because a lot of times students want to say, oh, x squared plus x, and technically that's x to the 1, right? Equals x cubed. But we have to be super careful. Another way you could have explained this would have been to say, actually, we'd have to do x squared times x to get x cubed, not x squared plus x, right? So those are the two main ways that would be important to use to reason through this. But either way, just remember this about exponents. Since exponents are based on multiplication, adding them does not let you combine into one single term. Certainly we can add these together, like once we plug the numbers in, like you can still add them afterwards, right? But you cannot combine them into one single term. Next, this is more direct review from our last video. Write a polynomial with the following conditions. If not possible, explain why. So let's look through these two things. First is a cubic polynomial. Remember, cubic means that its degree, right? And remember, that means the highest exponent in the whole polynomial is 3 for cubic. So just so we know, I'll write this here. This means degree is 3, and then B, linear, if you remember, means that the degree is 1. So we'll just remind ourselves of that. And now it says with 3 terms, all of different degrees. So each of the terms has a different exponent, right? Well, there's lots of options for this, so you can kind of check it yourself based on what I put for my own. But if it needs to be cubic, that means the highest degree is 3 exponents. So maybe I'll just be like, okay, 5x cubed. Or you could use a different variable like p or y or, any variable is okay. All of different degrees. So we need 3 terms though. Right now I only have 1 term. And a polynomial is the sum of different terms, right? Or you could have it minus. Let's use minus. Let's say minus 2x squared. And it needs 3 terms. I only have 2. Plus 5x, I guess. I guess I used 5 twice, whatever. Okay? I think we fit this. We've got 1, 2, 3 terms, and they all have different degrees, meaning different exponents, and the whole polynomial itself is a cubic, meaning it's degree 3. Okay? Now, you might notice, we're missing the constant term. Remember, the constant term is like if I had a number added on the end, like plus 8 or something, right? There's no variable with it. Although technically, you remember in our video that it's x to the 0, since that's technically equal to 1. But anyway, this has 4 terms. So no matter what we choose here, we have to leave 1 term out. A full cubic has 4 terms in it, but if I only want 3 terms, I need to leave one of those other terms out. I can't leave this one out because the whole polynomial needs to be degree 3, right? So, like I said originally, I could just leave that constant off. I could leave any of these off. I don't know. I could leave this like this and just do plus 8 and leave that linear term off, the degree 1 term. Anyway, okay, so there's an example and an answer for that. Let's talk about B. Linear polynomial with 3 terms, all of different degrees. So linear means degree 1, which means the highest exponent possible in the whole thing is degree 1. So let's try. I don't know, let's think of a number. Let's say 12x to the 1, right? Because degree 1, so that's going to have to be the highest. Plus, wait a minute, it's supposed to have 3 terms. I don't know if I can do that. Because if it's linear, and that's the highest, the only thing lower is a constant, like plus 7 or something like that. And the only way for me to have another term here is if it was like another constant or another x, because if I do like x squared, no longer linear anymore, right? So I kind of think that this is done. This is impossible. And how would we describe this? I guess we could say we can only have 2 terms if it's linear. And remember, I want to see that you have your own wording for what you said for this originally, not just only mine, okay? And that's probably the best way to describe it. I don't know, there's different things you could say. Now let's move to number 3. This one's pretty interesting because there's something else important about polynomials that is going to come up in this problem. So when it says plug in x equals 10 to the polynomial here, and what do you notice? Well, let's try this out. If you look really carefully, we get 5 times 10 squared plus 2 times 10 plus 8. Okay? And I guess my more official word I should have used in this is evaluate the polynomial at x equals 10, but we use plug in. I think we're familiar with that. And let's do this. Well, this becomes 10 squared is 100 times 5 is 500 plus 20 plus 8, which is just 528. And I want you to look back at that original polynomial. Maybe you didn't notice this yet or not, I'm not really sure, but now that we've looked at this, look really carefully. 528, 5x squared plus 2x plus 8. The 528 still stayed 528. Isn't that really weird? This actually is very related to different base systems with numbers, because we work in base 10. And so our digits, when we write numbers out, are based upon how many hundreds or tens or ones or thousands or whatever, each of the place values. And because those literally are the powers of 10, if we have a polynomial and we evaluate it when x equals 10, that's going to actually correspond directly to a number. And that's really kind of crazy. Now, there's some special things about it that, don't make it always going to be 528, 528, but that's just an interesting thing about them. So let's actually get into some newer stuff here and doing some operations on polynomials. A few, I guess, more basic examples and a couple deeper ones. First off, calculate the sum and product. Product is just review. Now let's remember, when we say sum, we mean we are adding the two things. Product means we are multiplying, okay? So in case you need to remember what each of those mean. So the sum is somewhat new, no pun intended, and the product is definitely something we've been working on a lot recently. So we have lots of tools. Remember, the product, if we're multiplying two expressions, means we need to distribute each with each, right? Each of these pieces needs to multiply with each of those pieces, and then we need to combine like terms, right? Quick side note, our earlier problem in our warm-up about, problem number 1, if you look at that, you'll notice that we said that you can't just add those two together. Those two we would say are not like terms, and because their exponent was different, and even though they had the same variable x, their exponent was different, right? So we couldn't add them together. And this is kind of going to be, a similar thing, especially when we're doing the sum and difference. So I guess, why don't you just go ahead and do the product as more practice on your own, and then we'll just look at it together. Okay, so I'm actually going to just work through this product in my head and see if I can do it. I'm going to need to do x squared times 8x, which is going to give me 8x cubed. And then I'm going to have a 2x squared plus 24x squared. So I'm going to have 26x squared. And then I'm going to have a 6x minus 32x, which is minus 26x. Interesting, those are both 26's. That's just coincidental. And then I'm going to have a minus 8 at the end. So that's actually kind of interesting that we have an 8 and 8 and 26 and 26. Again, that wasn't planned. But now, if you needed to, of course, maybe you used an expansion box or other way of distributing. X squared plus 3x minus 4, and then 8x minus 2. And hopefully you see where I got all my pieces. And I might have made a mistake, actually. This is the whole reason why I think expansion boxes are really important, because they organize it for you. You don't lose track of things. It's really easy to get lost when you're doing these ones. And I think, it looks like maybe I made a mistake because, oh no, I didn't actually, because that's a plus 2. I made a mistake writing it. So I guess I didn't make a mistake quite yet. And then 2 times 3x is 6x minus 32x minus 8. And then again, it's important you remember that always when you do these, the like terms will be lined up along diagonals for you, so it's easy to see which ones to add together to combine like terms. Okay, so we will get what I had there. Let's look at the sum. Now, just so you know, kind of like with numbers, if I want to add numbers, I'll often do, like if I wanted to add, I don't know, 23 plus 8, Well, 23 plus 8, I could just write it sideways, or I could line it up so that we have the place values match with each other, and then you can just add the 1s and then the 10s and go from there, right? Well, also with polynomials, it actually really helps to line up because polynomials have a place value as well. If you notice, we have my squareds, my first degree term, right? Second degree, first degree, and then my constant. So if we are adding or subtracting, we actually, it's helpful to stack them up on top of each other and line them up so their like terms all go together. So that's actually what we're going to do here. So I have x squared plus 3x minus 4, and then I have 8x plus 2, and it says to find the sum. I've got a little bit, I don't have that much space for my work, and I actually should be using my orange color. And you'll notice, okay, well, there is not a like term in the second one that goes with x squared. So if I'm adding these, then I'm actually just going to have an x squared there. 3x plus 8x is going to be 11x, and the negative 4 plus 2 is going to give me a negative 2. So the sum of those two polynomials is this. Calculate the following and combine like terms. So I have a sum here, and it looks like a difference here. This one's a little bit more complicated because you'll see that I have actually have a constant outside that needs to be distributed into each of those individual polynomials first. And then this one is a little bit more straightforward. So why don't you go ahead and take a stab on your own at both of these, please, and then we'll come back together. So please pause now. Okay, so reminder, it's really helpful to line them up like this, although if you're pretty okay with just seeing what the like terms are and just writing the answer, I totally understand that many of us are really comfortable with doing this, and that's totally okay then. But it does become helpful in later things if we do understand how this works, lining them up. So 8x cubed, you'll notice this is missing the squared term, right? Technically it has a 0x squared with it. And that's important because our other polynomial does have an x squared term. So they wouldn't line up properly if I didn't insert that 0x squared that's technically there. And so I'm going to do 3x squared plus x minus 2 here, and I'm adding those together. Okay? So at this point, since our like terms are already added up, and remember, this is exactly the same as place value when we're doing addition with just plain numbers, okay? Numbers are actually special instances of polynomials, really. Kind of like we saw in that last example in our warm-up, where we saw that the coefficients were exactly the same when x was 10. So let's do this. This just leaves me with 8x cubed, and then 0x squared plus 3x squared is 3x squared. And if you really actually wanted to here, you could technically say there's a 0x cubed in the second one, actually. So then we all see they line up. And then plus 4x plus 1x is 5x, and then negative 7 plus negative 2. Careful with your negatives. When you add two negatives, it gets more negative, so we have negative 9. Okay? So there's that one. You can check the other one. Now this is one where it'll be helpful to distribute first. Now, some of you may be wondering, should I distribute this negative 2 into everything, or just 2 and then subtract? Well, I want to remind you, adding the opposite is identical to subtraction. So actually you could do either one. If you wanted to distribute this negative 2 to everything and then make that adding, that's okay. Or you could just distribute the 2 and subtract. Doesn't matter. I'll do the second option. So let's distribute the 3, and that's going to make this 12x squared minus 27x plus 3. And we're going to subtract away. I'm going to tell you something. Please make sure you include parentheses, especially on subtraction ones, because it really helps remind you that all things are subtracting. So many times students forget and they only subtract the first thing, and then they end up adding the other ones. So just be really careful with that. Now if I distributed the 2, just only the 2, it's going to be 2x squared plus 20x, and then 2 times negative 6 leaves this one as negative 12. And then the negative turns into subtraction. But again, like I told you, if you wanted to distribute the negative 2 in there and then make adding, that's also okay. In this case, in any case, it's going to give you the same thing. 12 minus 2 is going to give me 10x squared. Negative 27, careful with negatives. Negative minus 20 actually makes it even more negative, so it's going to be minus 47x. And then 3 minus negative 12. Negative, negative turns into adding, right? So 3 plus 12 is plus 15. And there we go. Our final result is right there. So there's pretty much all the basic things about operations on polynomials. We've learned in the past products, but we did a review one. And then we've talked about the methods we would do for if we need to add or subtract them. You might be thinking, well, where's division? Division is a lot more complicated. We usually take care of dividing in a more advanced algebra class. So you will definitely learn that, but it will be in the future. Expand and combine like terms. So I chose this one in part because I want to remind you of an important thing that students try to do. And if you see x plus 1 squared, it still happens that we're trying to say, oh, we can just distribute that squared and we can say it's x squared plus 1 squared. But be careful, we can't. It means x plus 1 times x plus 1. And you remember that's going to have a middle term. So if we expand this, we're going to have x squared plus 2x plus 1. But then we have the minus x squared there. So in the very end, you'll notice something. I have x squared minus x squared. Those are like terms, and in fact, they're identical except opposite. So when you subtract, it's going to be gone. So this leaves me with just 2x plus 1, actually. Is that okay? Might be helpful to use parentheses just to remind that this became this, and then this was this. Now again, if you needed to use an expansion box for that, to get that, that's totally okay, but this is what we should get. We may want to use an expansion box for the next one, though. This one you might be wondering, well, how do I do 3 things? We've done multiplying 2 things before, but think really carefully. We actually already expanded x plus 1 squared. So this is actually x plus 1 squared times another x plus 1, and then we have that minus x cubed, minus x cubed at the end. So since we already know x plus 1 squared, we've already got that from the past, plus 2x plus 1, then that's multiply x plus 1, and I subtract x cubed. All right? So this is one I would encourage you to finish off on your own real quick, and then we'll do it together. So go ahead and do that now. All right. Well, if I'm going to use an expansion box, and again, maybe you don't feel like you need to, that's great, but I will do it myself for this. Then we're going to get x cubed, 2x squared, x, and then this is 1, so all those will be identical if you think about that. So that's going to just leave me with the same thing under there, right? So I'm going to distribute this x into there, I get this, and when I distribute that 1 into there, I get this. So in the end, what that becomes is x cubed, and then 2x squared plus another x squared is 3x squared, and 2x plus x is 3x, and then we have a 1. So I have x cubed plus 3x squared plus 3x plus 1, and then I have a minus x cubed there still, right? So there's my final expanded version of x plus 1 all cubed, and then let's just go ahead and combine this like term with that, and they cancel out again. So what I'm left with is 3x squared plus 3x plus 1 in the end of it. Okay? So again, that's going to be a pattern. That's actually going to be a pattern for a problem we look at in our next lesson. So I'm kind of leading up to that, or it's going to be related to it. But it's still good practice. Now let's actually get into using more of our vocabulary about polynomials and talking a little bit about sums and products some more. Now, I want you to think about something on the side. I guess I should have left myself some space here, but this is not part of this example. You can just put it on the side or just watch. If I had something like 3x squared plus 8x minus 1 times 2x cubed plus 5x squared minus 9x plus 10 or something like that, okay? Without even doing the whole product out, we can tell what the degree is going to be. We've already had these listed in the proper order from highest to lowest exponent. And I think you can agree with me that when I multiply this all out, we can at least see what the very first term is going to be. Because the first term of the result is going to be the product of the first two terms in the original polynomials. So I know that this polynomial is going to be 6x to the fifth plus blah, 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 a bunch of stuff. Okay, but all the other terms are going to be less than 5. So we can just do that in our head and say, oh, well, if I find this product, what's the resulting polynomial? What degree will the resulting polynomial have? Well, if that's degree 2 and that's degree 3, when I multiply them, it's going to become x to the fifth. Oh, the product is going to be 2 plus 3. The product polynomial is going to be a fifth degree polynomial, right? Now, let me ask you this. If I were to add these polynomials together, and again, just be with me and make sure you're just understanding what we're talking about here. So instead of multiplying, if I were to add them, then what would happen? Well, this adding is about all about like terms. Multiplying, you have to do like terms like along the way, but the main thing to think about the degree was what's the product of the first terms. But if we look here, if we add these together, this is degree 3, this is degree 2. So the squareds are going to have to add together because they're like terms, and then the x's, the linear terms, and then the constants. This has a cubic, degree 3. This one doesn't. So you can see what if we actually added this together, what would the degree of the result be? Well, the degree of the result, if you think about it, since this is going to have to stay along there, can we like raise the degree by adding? No, because whatever the highest one just stays there, right? And so multiplying two polynomials increases the degree. But if you're adding two polynomials, we don't really change the degree for the most part. There is a special case that we might have that happen, but we'll actually see that in one of our examples. So let's finish this off all the way and answer this one. So what we're saying is you need to come up with two polynomials that fit these descriptions. So when we add them, the degree is 3, and when we multiply them, the degree is 6. I'll just do this one for you. We could make a polynomial with all the terms, but really what matters in all of these is actually whatever the highest, the leading term, right, the first term is. So here's an example. If I had 2x cubed and 6x cubed, these are both individually polynomials. Of course, we could have more terms in them, but like I said, just the highest term is what is going to matter for most of these. And watch what happens when I add them. 2x cubed plus 6x cubed will be 8x cubed, and so that still stays degree 3, right? But what happens when I take their product? 2x cubed times 6x cubed is going to give me 12x to the 6th. And so its product is going to have degree 6. So now that we've kind of talked through that one together, why don't you go ahead and try to take a stab at the remainder of them, and then that'll be it for our lesson today after we go through those. All right, so again, these are open-ended, so you may not get the same answer as me, so it's important that I see you have your own answers, not just these, okay, when I check this. So sum degree 3, but product degree 5. Wait a minute, this looks a lot like our first one. How could we have our sum of degree 3, but our product be degree 5? Well, product degree 5, let's just try that out. What if I reuse my 2x cubed, and maybe I can reuse the 6, but the x, whoops, excuse me, this should be cubed. But if I want the product to be degree 5, if that's 3, this should be 2, I think, right? Let's see if this still works. If I take their sum, well, these aren't like terms. So their sum is simply 2x cubed plus 6x squared. Is that overall still degree 3? Yeah. And their product, when I multiply them, becomes 12x to the 5th. Oh, it works. Okay. So they just can't have the same degree anymore like they did up in part A. Let's look at the next one. Sum of degree 2 and product of degree 2. This one seems kind of weird right now. So if I need the sum to be degree 2, then maybe I come up with like, I don't know, negative 11x squared. and 4x squared. So I add these and it's going to still be x squared, so the sum is degree 2, but I think I made a mistake because the product needs to be degree 2, but this product is going to be degree 4, so that's not going to work. Oh, I see. Wait a minute. What if I just left this to be a constant number? Because even if I add these, they're not like terms, so negative 11x squared plus 4 is just separate, but that whole thing is still degree 2. But when I multiply these, the 4 does multiply to this and it makes it negative 44x squared, and that's still degree 2, so okay, I think that works. Let's try part D. Sum of degree 0, wait a minute, sum of degree 0. What is degree 0? The exponent is 0. Oh, exponent degree 0 means that the x to the 0, so x to the 0, that just equals 1. So if I had like 3x to the 0, that's the same as just like saying 3 times 1, which is just 3. I see, okay. So I need to have just a number left when I add them, I guess. That's what we mean when we say sum degree 0. But if I need the product degree 4, that almost seems like this almost seems like impossible, but I think I came up with something. Watch this. If the product needs to be degree 4, I'm thinking like, oh, yeah, I think I know. I'm going to make them both degree 2. There's some trickery here. If I had 3x squared and negative 3x squared, watch this. When I add these, they're opposites, so they just cancel out and you just end up with 0. But when I multiply them, I get negative 9x to the 4th, and that'll work. I could even just have a number if I wanted to on here, or another term. I could have plus 2x, plus 9 or something like that. And when no, actually I couldn't have the 2x, because even though these cancel out, you're going to still have that linear term that's going to be degree 1. But I could have a constant. I could just have that plus 9 there. Because then when I add these cancel out, and I'm just left with the number, which is degree 0 itself. But then when I multiply them, it still is degree 4. So that'll work. And then last but not least, we're going to get to where I said if not possible. This one actually ends up being impossible, and it should make sense, because if we have a sum that has higher degree than the product, that should work out. Remember how the product raises the degree, and the sum can be a lower degree, like we saw here. You can actually drop in degree, but you can never raise in degree if you're taking a sum of two polynomials. So this one actually, you can try to play with it as much as you want, but it turns out to be impossible. So, happy math. There is our lesson on operations on polynomials.